Today we're looking at Think3D, Thinking with Space for Spatial Reasoning, a paper from Zebin Zhang and colleagues at Dalian University of Technology, UC San Diego, and Oxford.
And this one tackles a really critical flaw in current vision large models. I mean, models like GPT-4V are incredible at 2D analysis, right?
For sure.
But they completely fall apart on genuine 3D spatial reasoning. Things like navigation, multi-view understanding, because they just see a flat grid of pixels.
So the solution here is Think3D. It's a training-free framework, which is key, that basically upgrades a VLM from just a passive observer to an active 3D explorer.
It reconstructs a point cloud from the images you give it and then lets the model walk around the scene with a virtual camera.
And the results are pretty wild. Without any extra training, it boosts GPT 4.1's performance on benchmarks like B-Link and MindCube by over 7.8%.
But the really interesting part, I think, is Think3D RL.
Right. Because for smaller models that don't know how to explore, they introduce a reinforcement learning policy. It literally teaches the model how to move the camera to find information.
And it closes that gap between the small open source models and the huge proprietary ones. It's a move toward, genuine system 2 thinking for these models.
Okay, so that's the high-level summary. Now let's really tear this apart, because if you're working with VLMs or maybe building ARC pipelines, this idea of active exploration is a huge shift.
Oh, it's a massive shift from the usual feed an image and pray approach.
Totally.
It all starts with what the paper calls the 2D perceiver trap. We see these models getting amazing scores on benchmarks like MMMU, and we assume they understand the world.
Right. You assume there's some geometric intuition there.
But there isn't, really.
Yeah.
The authors draw a line between semantic understanding, knowing that's a chair, and geometric understanding, like knowing that chair is facing away from us.
Because to the VLM, it's just a grid of tokens. It's a flat surface. Any concept of depth or occlusion is, well, it's basically hallucinated from correlations in the training data, not from first principles.
Exactly. And they contrast Think3D with what they call think with image methods. You've probably seen agentic frameworks that give a model, like a zoom tool or a crop tool.
Or even something like a depth estimation map.
Right, but a depth map is what we'd call 2.5D. It gives you relative depth, sure, like a Z buffer in a video game, but it's still tied to a single viewpoint. It doesn't tell you the global structure.
Yeah, a depth map of my laptop from the front won't tell me what ports are on the back.
But a 3D mental model would. And that's the whole cognitive inspiration here. Humans don't just, stare at a static image on their retina. If you're in a maze, you don't calculate the whole layout from one frame. You move. You integrate different views over time.
And that integration process is exactly what Think3D is trying to give to the VLM. It's turning it from a static classifier into an agent that can operate in a real 3D coordinate system.
So let's get into the architecture, because the 3D manipulation toolkit they built it's a serious piece of engineering. This isn't just clever prompting.
No, you're building the whole virtual environment for the model to play in.
It kicks off with the 3D Reconstruction module. They use a method called Pi3, which is short for Permutation Invariant 3D Reconstruction.
Okay, so for the engineers listening, why Pi3? Why not just a standard photogrammetry pipeline or, say, a NERF?
It's about speed and generalizability. Pi3 is permutation equivariant.
Meaning the order you feed the images in doesn't matter.
Exactly. It robustly figures out the camera extrinsics, so where each photo is taken from, and then generates a sparse colored point cloud. And critically, it's fast enough to run inside the reasoning loop.
So the VLM gets a query and boom, the system builds this 3D representation. Now the model has to actually interact with it.
And this is the 3D transformation step. This is where it gets really interesting for anyone building agents. The VLM had to output specific commands to move a virtual camera. It predicts rotation angles, azimuth for horizontal, elevation for vertical.
But that brings up a huge technical problem, right? Coordinate systems. If a model just says, turn left 45 degrees, what does that even mean? Left relative to the world, relative to the camera.
That is what they call the anchoring problem. And you're right, LLMs are notoriously bad with absolute coordinate systems. They just drift. So Think3D does something clever. It uses the camera positions from the original input images as anchors.
So the model says, start at the position of camera 2 and rotate relative to that viewpoint.
Precisely. It grounds the abstract command in the physical reality of the input data.
Okay, so it moves, and then it has to see the new view. That's the novel view rendering part. And they make this distinction between a global view and an ego view, which feels very, like, game engine-y.
It basically is. The The global view uses an orthographic projection. Think of it like a blueprint. It removes all perspective distortion. It's that God's eye view, which is mathematically way better for understanding layout and where things are relative to each other.
Whereas the ego view is the standard perspective projection.
Exactly. Ego view is what a real camera lens would see. And it's crucial for occlusion tasks. If the user asks, "Can you see the coffee machine from the doorway?" The global view is useless because it sees through walls. You need the ego view to see if the fridge is blocking your line of sight.
So we have the environment, we have the controls. Let's talk about the actual loop. They frame it as an iterative chain of thought process. Observe, manipulate, reflect.
It's a classic agentic loop, just applied to geometry.
Right.
So step 1 is input. The model gets the images and the user's question.
And step 2, decision. And this is important. The VLM has to decide if it even needs the 3D tools.
Right. It filters out easy questions. You don't want to waste compute spinning up a 3D reconstruction if the answer is obvious from the first image.
Okay, but if it decides it does need more info, it goes to step 3, action. It picks an anchor, chooses the rotation angles, and selects a view mode.
Then the system renders that new image, let's call INU, and just appends it right back into the context window. And that leads to step 4, reflection. The model looks at the new image and thinks, did this solve my problem? If yes, it answers. If no, it goes right back to the action step.
They have this perfect example in the paper that makes this whole loop click the mug case. It's a classic computer vision ambiguity problem.
The mug ambiguity. So you have 2 pictures of a mug that has a bicycle printed on it. In image A, the handle is on the right. In image B, the handle is centered. And the question is simple. Did the camera move? Or did the mug itself rotate?
And just looking at the 2D images, the optical flow could be almost identical. It's really hard to tell.
Right. A normal VLM is just guessing based on priors. But the Think3D agent, it does something specific. It requests a global view, top down. So azimuth 90, elevation 0.
And because the reconstruction already calculated where the cameras were, the top-down render can actually show little camera icons in the 3D splines.
That's the key. It visualizes the trajectory. It shows camera 1 is over here and camera 2 is over there. It geometrically proves that the camera moved counterclockwise around the mug. The ambiguity is gone, not by guessing from pixels, but by inspecting the layout of the scene itself.
That's proper System 2 thinking. It's not intuition, it's verification. But this brings us to what I think is the most fascinating part of the paper, the exploration gap.
Yeah, this is where you see the difference in model capabilities really starkly. A model like GPT 4.1 is just smart enough to have a world model. It knows that if it wants to understand a layout, it should probably fly the camera up and look down.
But the smaller models, the 7 billion or 4 billion parameter models?
They're completely clueless. The authors tested this on Qwen 3 VL4B. You give it all these amazing tools and it just drifts. It rotates the camera randomly. It requests views that show nothing new. It has the engine, but there's no driver.
So enter Think3D RL. They decided to train an exploration policy. And for the ML engineers out there, the algorithm they used is Group Relative Policy Optimization, or GRPO.
And the training setup is so cool because the reward signal was incredibly sparse. They didn't do imitation learning. They didn't show the model, here's the correct trajectory.
They just rewarded it for getting the final answer right.
Purely outcome-based. There was an RAMS, reward for answer, and a tiny RFMT, reward for formatting. The model had to figure out, entirely through trial and error, which sequence of camera movements was most likely to lead to a correct answer down the line.
And the emergent behavior is it's wild.
It really is. The model rediscovered the top-down strategy all on its own. Before RL, the policy was just noise. After RL, that little 4B model developed this huge preference for requesting elevation 60, azimuth 0, basically, a drone shot, whenever it was faced with a layout task.
It learned that altitude equals context.
It learned a human-like cognitive heuristic completely from scratch. And there's a neat engineering detail here about how they made this training practical.
Right, because rendering point clouds constantly in an RL loop would be insanely expensive.
Way too expensive. So during training, they discretized the action space. The model could only choose from 3 canonical views, top, left, or right. This massively cut down the search space and the compute.
But at inference time, it's not stuck with just those 3 options.
Nope, and this is the cool part. It generalizes back to continuous control. It learned the concept of relative movement. So during inference, it can fine-tune the angles. It's a great example of training on a simplified task to learn a much more general capability.
All right, let's hit the benchmarks. We need to see if this actually moves the needle. They used BLink, MindCube, and VSI-Bench.
And the numbers are Pretty undeniable. Let's start with the big proprietary models, GPT 4.1. By just plugging it into the Think3D framework, no new training at all, it gained 27.09% on the B-Link benchmark.
A 27% jump on a benchmark. That's usually the kind of leap you see between entire model generations. That's massive.
It completely changes how useful the model is for these kinds of tasks. And on MindCube, which is more about complex rotation and reasoning, it saw an average improvement of over 11%.
But the open source results are what really sells the RL part of this.
This is the A/B test that matters.
Yeah.
Before RL, Qwen3 VL4B with the Think3D tools only gained 0.7%. That's just noise. The tool was useless because the model didn't know how to use it.
And after the RL training?
The gain jumped to 6.8%. It went from a flat line to a really significant performance boost. And that proves the bottleneck for these smaller models isn't always their ability to process visual data. It's their executive function, their ability to decide how to gather that data in the first place.
I want to touch on the ablation studies quickly because they debunk a really common assumption, the whole static 3D idea. Why not just generate the point cloud once and feed the whole thing to the VLM? Why bother with the active camera?
You'd think that would be better, right? Just give it all the 3D data at once. But in some cases, performance actually dropped.
Information overload, the context window problem.
Exactly. A raw point cloud is noisy, it's unstructured. If you just dump that into a VLM's context, it struggles to apply its attention mechanism to the relevant parts. The act of exploration acts as an information filter. By choosing a specific view, the model is isolating the signal from the noise. It's focusing its limited attention on a relevant slice of reality.
Let's walk through one of the complex reasoning examples to really nail this down, the green cabinet scenario from MindCube. This one is a real logic puzzle.
Yeah, this one's a headache. So try to visualize this. You get 3 images of a room. All you're told is that image 2 is facing a window. The prompt asks, if I stand at image 2's location, face the same way, and then turn 180 degrees, what is to my right?
Okay, so mechanically that's teleport to camera 2's spot, face the window, spin around, and then look to your right.
Correct. Now try doing that with 3 unlabeled photos. It's almost impossible for a human. But the Think3D model, its first move is to request the top-down view, elevation 60.
It goes to its happy place, the strategy it learned.
It goes to its safe spot. And from that top-down view, it sees the layout of the cameras. It sees they form a triangle. It identifies camera 2 facing the window. It sees camera 3 is on the opposite wall, facing the other way.
So it's deducing the geometry of the room based on the camera positions.
It deduces that if you're standing at camera 2, but facing the direction of camera 3, then what's on your right is the same as what was on camera 3's right. It locates the green cabinet in that vector. It solves the puzzle, not by matching pixels, but by reasoning about the spatial relationship between the observers.
That is so clearly System 2. It's slow, methodical reasoning.
It's reasoning about the process of observation itself, not just the observation.
So looking ahead, this paper really feels like it's suggesting that spatial intelligence isn't just a data scaling problem.
I think that's the #1 takeaway for researchers. For years, we've been trying to solve this by just throwing more videos, more 3D assets, more data at the models. But Think3D suggests that maybe agency is the missing ingredient.
It's the difference between watching a YouTube walkthrough of a video game and actually holding the controller.
That's a perfect analogy.
Yeah.
And the success of the RL component on that small model just opens up this huge door. I mean, if we can use RL to teach a 4B model to use a virtual camera, what other cognitive tools could we teach it to use?
A physics simulator, a code interpreter to run experiments.
A search engine, a calculator, a formal logic verifier. We're moving from models that just retrieve and rephrase information to models that can actively investigate the world to generate new information.
It points to a future where maybe small, specialized models trained via RL to master a specific tool could outperform giant generalist models on certain complex tasks.
It's that agentic future we all keep talking about, but applied to the internal reasoning loop, not just external APIs. And it's training free for the base VLM, which makes it immediately useful. You don't have to retrain GPT-4, you just wrap it in this active loop.
For those of you who want to dig into the implementation, and I really recommend checking out their trajectory visualizations. They're super cool. The authors have released the code.
Yeah, you can find it all on GitHub. Just search for VSI-Bench. The repo is really well documented.
And that wraps up this edition of AI Paper Podcasts. This work from Zhang and the team is a really significant step towards getting our VLMs to, actually understand the space they occupy, not just describe the pixels they see.
It's a fantastic paper, a highly recommended read.
We will see you on the next one. Keep building.